was surfaces. You know better than.
There's written geodesics in the.
Ah, really? Yeah. Wow. Okay.
So now you have to change topic.
Yeah, I will change now. Yeah.
I was surprised because I didn't understand what it means.
Yes, right. Yeah, it's a great pleasure to be here, and especially on this occasion. I have to admit that I didn't know Sasha kind of as everybody else here for 20 years, or we met like, no, it was 20 years ago, really, in Stockholm. 25 years. But for me, before that, he was just a name in the kind of textbook, like absolutely classical, and it was surprising to see these people alive, you know. So. And then, yeah, and kind of when we met first, it was kind of great surprise to see that not only he is alive, but he is kind of very enjoyable person and very genuine and fantastic. So not only great mathematician, but excellent human being. So yeah, I just excuse to explain my choice of topic because also my co-author Leonid Chekhov is a great friend of Sasha, and we want to present something that we did together, despite that it's probably not very close to kind of interests. But I hope so might be found some interesting here. So going to the talk, so what is the main message? Kind of, I'm doing for many years something which is called cluster algebra, which for this crowd is kind of nice coordinates in algebraic Poisson variety. So you can think about that as some sort of choice of nice Darboux type coordinates for Poisson variety. And it's always useful to find Darboux coordinates for the purpose of quantization, and kind of you know better than me. And such choice of Darboux coordinates was known for ages for Teichmueller space of surfaces with boundaries. So this was explained, probably Penner did it first, right? So if you just choose triangulation of the surface, then you can assign to each side of triangulation some parameter. I will explain it in more details in the future, and it will give, if your triangulation is geodesic, then it gives you some parameterization of Teichmueller space, and these parameters behave nicely when you change triangulation. So, but this simple recipe surprisingly breaks when the surface is kind of closed, no boundaries, because nobody knows how to construct triangulation by some really very stupid reason. So you don't know what are vertices of this triangulation. And this question back people, so first attempt, well, there is kind of natural way to do it. So you just pretend that you have triangulation, you introduce some fake vertices, and then you kind of create triangulation with fake vertices, and then you require that monodromy around this triangulation is trivial. But kind of then you have to get rid of this fake point, and this lead to very non-trivial Hamiltonian reduction process, which was not known how to do. Kind of the first approach was probably done by Francis Bonahon, and he managed to kind of finish this approach for torus with just with one puncture. And kind of, so what we try to solve different question to introduce some nice coordinates for something which is called symplectic groupoid, and then as a byproduct, we discovered sort of cluster coordinates for Teichmueller space of closed genus 2 surfaces, and that is what I want to.
So do you mean that there is no canonical choice of triangulation, and that's.
Yeah, exactly, right. So, and if it's non-canonical, you have to explain how to kind of. Okay, so kind of our approach is kind of we utilize connection between two natural Poisson varieties. One is symplectic groupoid of unipotent upper triangular 3x3 matrices, which was known from kind of work by Bondal and simultaneously Dubrovin, Ugagle, and I don't know, Marta, were you involved in that, or to kind of equipped with natural Poisson structure, Poisson bracket. And second is Teichmueller space of genus 2 closed Riemann surfaces, which is equipped with a natural Goldman bracket. So first, let me describe what we use this term log canonical coordinates. So it is, we have collection of functions. I denoted here the I. Oops. Sorry. The I. And with conditions that Poisson bracket between the I and the J is some constant times the product. It's a simple modification of the usual kind of Darboux coordinate. And why it's useful? Because kind of by Darboux theorem, Darboux coordinates exist only locally. So if you have like algebraic variety with algebraic, say, quadratic Poisson structures, then it's natural to ask if you can find such Darboux type coordinates, which are kind of global regular functions on your variety. Say your variety is affine. And in some examples, these log canonical coordinates behave better. So you can find global log canonical coordinates, but you are unable to find Darboux coordinates. And these examples include, say, kind of Lie groups, standard Lie groups, and Poisson Lie brackets, which is kind of essential for us. And also, if you consider a affine variety, you take Grassmannian, you take affine cone over Grassmannian, and then you can induce some Poisson, induce bracket from homogeneous bracket from the compatible with the action of the corresponding parabolic subgroup. So it also has this type. So there are kind of nice log canonical coordinates, but there are no Darboux coordinates. So here is example of these log canonical coordinates. And what I want to mention that it's also natural to assign with variety with such log canonical coordinates a quiver. Quiver is just directed graph. And if all these omega ij are integers, then we use kind of, here is a quiver. So the quiver just encodes the Poisson bracket between the i's, such that omega ij in this formula is just number of arrows from I to j minus the number of arrows from j to I. So here is a formula. For example, this one is so-called famous Markov quiver, and this is a corresponding Poisson bracket. Okay, Teichmueller space, it's kind of everybody knows. It's just introduced notation. Sigma GS is topological genus G surface with S holes. Teichmueller space parameterized hyperbolic structures. And well,
Logarithmic singularity at the points. Yeah. Riemannian metric. It has a cusp. Yes.
You might have a cusp, yeah. But we allow holes also.
Holes, but if you have a point,
Yeah.
then it should have a.
Yeah, right. And then with a loop gamma, we assign a function on this Teichmueller space in the following way. So if you have a loop, then we can consider the element of the Fuchsian groups, kind of monodromy along this loop, and we can take trace of this monodromy, absolute value of the trace of monodromy. So trace is not very well defined because the element of Fuchsian group is given by up to multiplication by plus minus 1, but absolute value of the trace is well defined. And this is called geodesic function. So to describe geodesic function, you just give the corresponding element of homology. Then it's known that Teichmueller space is equipped with Goldman-Poisson bracket. Well, I'm not going to explain what it is. And kind of let me probably, and there are also nice shear coordinates after William Thurston, which kind of this log canonical coordinate with respect to the Goldman-Poisson bracket. So
So I didn't understand. So I'm familiar with Poisson bracket if you do not put absolute value for oriented loops. But if you have non-oriented loops, how do you define?
well, I will give the formula. So it's
It doesn't depend on orientation.
Why is it absolute value then?
Where did you see that?
I mean,
well, just this element is defined up to kind of plus minus one. How
They're
you
thinking in PSL2. They're thinking in PSL2.
it's the element of
Okay.
PSL2.
Yeah.
Okay. So, well, let's lift. Let's consider the lift to universal cover. So then geodesic is kind of well, ideal triangulation is kind of triangulation formed by these half circles. So any ideal triangulation of the surface is lifted to such infinite ideal triangulation of half plane. And we can assign to, well, this diagonal of this ideal quadrilateral, the corresponding cross ratio, which is defined like that. So, and point is that these parameters describe you how you can glue your surface out of this ideal triangle. So all ideal triangles are equal to each other, but the only kind of model is that you have is how you glue two ideal triangles to each other. Right, and this is exactly described by this cross ratio parameter. So this collection of parameters is sort of nice parameter space on the Teichmueller space, and they known as well, exponential shear coordinates. And if you change triangulation, for example, you can take this diagonal, erase it, and replace it by the second one in the same quasi triangular, which is called flip. Then these parameters, well, they changed under very simple transformation. I probably kind of show it later, and this leads to this cluster algebra picture in parameters. Goldman-Poisson bracket has very simple expression in these coordinates. A Poisson bracket of xi xj is just some constant epsilon ij times the product xi xj, where epsilon ij is just some adjacency index between two sides of triangulations. Well, since it's not very important, I probably skip drawing what it is. So, but it's kind of, in most cases, it's plus minus 1 or 0.
why does it need to have a boundary for this?
Because, well, it's you have to deal with ideal triangles. How you do ideal triangles?
All points are on the boundary.
Yeah. And kind of the question is, natural question is, find cluster type parameters for if there are no holes, if there are no boundaries.
So for parameter is attached to an edge, and the number of edges equals to the dimension.
Yeah, if you kind of allow kind of holes.
Minimal triangulation.
Exactly right. If you also allow holes to go like to change the size of the holes. Okay, that is one object, and I hope I formulate the question. Now, second object is symplectic groupoid, is the space of unipotent upper triangular n by n matrices. Well, sorry, let's denote by this an the space of unipotent upper triangular real matrices, and then symplectic groupoid of upper triangular matrices by, according to Alexei Bondel, is the following. It's a collection of pairs, EA, where B is like any square n by n matrix, and A is unipotent upper triangular matrix, which satisfy compatibility condition such that PAB transpose is also unipotent upper triangular. So idea is that you think about this element as sort of triangular form, and B is a linear change of coordinates, which preserves the shape of triangular form. So if you compute the matrix under the change of coordinates, it's still unipotent upper triangle. Then it was it is equipped. This thing is something which is called symplectic groupoid according to definition by Ellen Weinstein. It's equipped with symplectic form, which is sort of canonical in the following sense that if you consider the fiber product M2, like which is the set of all compatible pairs, so TA, and then second pair is kind of CBA transpose, then there is a natural product map from this fiber product to M when you just take composition of the corresponding. Like B is natural to consider as sort of morphism, A is an object, so you take composition of two morphisms. And well, there are also two projections. Kind of M2 is a set of two pairs, two compatible pairs. There are two projections: projection to the first pair and projection to the second pair. Then symplectic structure omega satisfies this defining property that the pullback by product map is decomposed into pullback by the first projection by plus pullback by the second projection.
This works for any reductive group? This kind of thing.
It's more general, yeah.
You can use for B transpose, you can use W0 conjugation.
Yeah, that it's So and M is equipped kind of well, then you can do the following. So you can take this symplectic form on M, consider the dual Poisson structure, and push forward this dual Poisson structure on the space of object by the first projection. Like M is a set of pairs, BA, and then you can project this BA just to A. Then this push forward kind of induce a Poisson structure on the set of upper triangular matrices, and this is exactly the Poisson structure that was studied by kind of Dubrovin, and Bondel wrote explicit expression for the Poisson structure. That in particular, well, this is example for n equal 3. So the matrices look like that: 1, 1, 1, x, y, z, and in particular in these coordinates, the expression for Poisson bracket looks like that. You see that the non-homogeneous quadratic, and if you forget about the linear part, then these coordinates x, y are exactly log canonical. But the linear part spoils this log canonicity, and the question: can we find log canonical coordinates for upper triangular matrix? So for us, it's log canonical. It's a little bit better.
How many other Poisson structures on the upper triangular matrices?
There are, but What can I say? So we are interested in that one. Um,
Does it have to do with the Drinfeld-Poisson-Lie structure on like big cell of your group?
well, I will, yeah, it's, it's one of the points. You are kind of ahead of me. Yeah, we'll discuss it. So, well, yeah, so the facts from Bondle's work that corank of this matrix is integer part of n over 2. And you get independent set of Casimirs, for example, by doing that. You consider the following: matrix A plus lambda A transpose, and then take its determinant, some sort of characteristic polynomial. And this characteristic polynomial is reciprocal. So the independent coefficients of this reciprocal polynomial create collection of independent Casimir functions. For example, for n equal 3, you will have just n equal 3, so 3 divided by 2 is 1.5, integer part is 1. So you will have one Casimir, which look like that. And this is very special function for us, which it's called Markov function, which we'll kind of discuss later. Well, Markov function is kind of slightly modified and constant, and it's Casimir function. Well, again, as I said, so the question is how we can recreate log canonical coordinates on really on A. Idea is let's try to use morphism to parameterize this pair. Let's try to use matrix B to parameterize pair BA. So in other words, if B is given, can we find such unipotent upper triangular matrix A such that BA B transpose is also unipotent upper triangle? And let's do exercise. So if take 2 by 2 matrix, this I did by myself and very proud by. So we did computation, so we get this element, and in particular we see that if you want this element to be equal 0, then A12 is expressed in terms of B's. So if B is given, then there is unique solution for A. Right? Then we can substitute this solution for A in diagonal elements, and we will get this condition, which can be satisfied, right? So in particular, we see that not for any B, we can find the corresponding matrix A. So to find the matrix A, we need these two elements to be equal to 1. And it implies in particular that, this condition determine, this is particular case, there are several solutions, but this is one particular case. Determinant B is equal to 1, and this ratio is equal to -1. It's easy to understand from this equation that both coefficients are equal to 1, that square of determinant is equal to 1, but let's choose just one case, like determinant B is equal to 1, and then B12 divided by B21 should be equal to -1. And for higher n, we obtain the following result, that not for any B we can find compatible matrix A, but B must satisfy some conditions, which look like that. Determinant, one set of conditions that we can consider, that determinant B is equal to 1, and the kind of, for any such decomposition, block decomposition of our matrix in such that this is a block of size k by k, and this is block size by n minus k by n minus k, the ratio of the corresponding determinants is -1 power n minus 1.
And what is B hat?
This is this block, right? Well, first of all, this is typo because I forgot to erase it, and it just means here that it is this block. so if our metric satisfies this condition, then there exists exactly unique unipotent upper triangular array such that the pair is compatible. So we have some subset in non-degenerate matrices which parameterize the collection, well, this symplectic group one. Why it's kind of interesting? Because I think especially for you, this ratio is kind of very well known in Poisson geometry, right? So this is Casimir function for the standard Poisson Lie group in JLN. Right, so we have ideas that standard Poisson Lie group in JLN has something to do with kind of with the whole this business. And indeed, so kind of when we fix our ratio to some particular values to -1 power n minus 1, so it just means that we consider some particular general symplectic leaf of this standard Poisson Lie structure in JLN. So in this particular symplectic leaf, which I denote here by GL not, JLN circle is well kind of parameterizes, at least birationally, our symplectic leaf.
Is this symplectic leaf of specific dimension, or is it the
We
general?
will come to. Yeah, no, it is kind of, this is general.
But the Casimirs are said to be particular numbers.
Yeah,
but
exactly right.
How do you get that this is a general leaf? I don't.
Full dimension.
Full dimension. I don't know how to explain. It's full dimension. We will count.
General in the sense of
Generic.
in
Generic, yeah,
yeah.
generic, yeah.
So under Semyonov-Tenishansky map, this should correspond to a conjugacy class. So this is conjugacy class of what? Under the dressing, so that the
Well,
Exercise for this afternoon.
yeah, maybe, yeah. Not ready to answer. Okay, so, and we can consider the following map. So we can consider the map phi from this GLN circle to the product AN times AN. So where kind of we know that matrix A is uniquely defined, and we can consider the second matrix A tilde, which is kind of the target of our morphism. It's B transpose. So this product AN cross AN can be equipped with a product Poisson bracket. AN has Poisson bracket, and this product can be equipped with a product Poisson bracket, and claims that this map is Poisson. So sort of the standard Poisson Lie structure on B kind of is pushed forward to the Poisson structure on this product. Now let's do some dimension count. So GLN circle is, well, let's kind of consider the case n equal 3. Then it's 3 by 3 matrices. And for 3 by 3 matrices, we have 3 conditions. We have determinant is equal to 1 and 2 other conditions that I mentioned, like this 2 ratios is equal to -1. So totally we have codimension 3, so dimension is 6. And dimension AN cross AN is also 6 because it's 3 by 3 upper triangular matrices. Each is 3-dimensional space. However, it's not true that the image of our map is 6-dimensional because the matrices A and A tilde satisfy one relation. So what is this relation? So let's recall our Markov element. And kind of Markov element of A, it's determinant of A plus A transpose divided by 2. So it is this thing. And that it's another proof that kind of, I think Arnold said that each talk must have one short proof. this is a proof that I am kind of ready to. There, so kind of M A tilde is 1/2 determinant A tilde plus A tilde transpose. So kind of we replace A tilde by this expression. We see that determinant B square is factored out, and determinant of B square is exactly equal to 1. So we see that Markov element for A must coincide with the Markov element for A tilde. And the image of our map is 5-dimensional. So we have like Poisson map from 6-dimensional non-degenerate symplectic ink into something 5-dimensional. And later, kind of now let's discuss what is connection of these two cluster algebras. Kind of to do cluster algebras, we use our map as excuse to introduce cluster algebra in the space like A cross AN cross AN. Because by work of Volodya Fok and Sasha Goncharov, the space of all non-degenerate metric, no, not by your work, by ancient work of other people like Fomin, Zelvinsky, Berenstein. This space is equipped with cluster algebra structure, but it's convenient to use Fok and Goncharov coordinates to describe cluster coordinates of this space. Now, I won't torture you very much with definition of cluster structure, but kind of how these parameters look like. So we can draw such a mesh, kind of triangle, and then this graph, and then, well, faces of this equipped with some parameters with kind of labeled by pre-indices, barycentric labeling. And if we take the dual quiver to this graph, so it will describe Poisson bracket on the space of parameters. Now, such collection of parameters describe us how to construct upper triangular metrics, really many upper triangular matrices. And well, with the bracket here will induce some nice bracket on the space of upper triangular matrices. So first of all, how one can assign to the set of parameters some upper triangular metric. So let's just follow, sorry, let me recall here. So here is oriented graph. And in the oriented graph, we can take oriented paths going from the right side to the left. So let's take one of these paths and assign a weight to this path. The weight is just product of all parameters above this path. And now let's make the matrix. So the transport matrix is Tij is the sum over all paths going from J to I. Sum of the, well, weight of sum over all paths going from J to I, weights of such path. A simple computation, which I'm not going to do, is that our simple Poisson bracket for parameters induce the standard trigonometric Poisson-Lie bracket on GLN. And then in particular on our symplectic leaf GLN naught. So now let's play the following game. Let's take, well, one triangle define as like three matrices, like 1, 2, and 3, like going from from right side to the left, from left side to the bottom, and like that. And then we can take the same matrix, flip it around, like, and then join them together. We will have like 6 triangular matrices in such way. Well, this is example. So if you just introduce this parameter on the matrices, say matrix T1 has the following form in the parameters. And this is matrix T2, which is this one. It has this form. And we will use this construction to describe sort of kind of reduce the definition of reduce the solution, sort of parameterize matrix B. Kind of we will recreate the solution of well, description of this symplectic groupoid in terms of such such pictures.
It's totally positive the way that it's parameterized like this.
Yeah, it's exactly this parameterization which describes the parameterization of totally positive.
Totally positive, yeah.
Yeah, exactly. So in these terms, if we if we use this, we can construct matrices T1, T1 bar, T1 tilde, and T2, T2 bar, T2 tilde in terms of parameters. And then let's introduce matrix S, which is like that. Kind of, it's plus minus ones along the secondary diagonal. And then we can kind of construct matrix B, which is just product T1, T2. So it's sort of transport matrix from this right side to the left one.
So you missed a twiddle or because B should be T2 twiddle T1 or T2 bar.
No, T1 is this one,
Yes.
T2 is this one.
Ah, sorry.
Yeah, no, it's
I was putting twiddles on one triangle.
unexpectedly for me, I am correct this time, so no typos.
Sorry.
And this is B, and matrix A can be constructed in the following way. So you take S, then T1 transpose, kind of T1 tilde goes from bottom to the right side, and transpose is sort of, you have to understand the transpose sort of arrow in the opposite direction. Kind of, so you're going this way, and then bottom side is glued to the top one. And then we continue kind of going back like this one. So it sort of look like a loop. Well, here picturally shown by this yellow. Well, if you just do, it's easy to see that A is upper triangular just by looking at the form of all this, at the shape of all these matrices, and the A tilde, which is B transpose, also can be kind of computed, and that's also upper triangular. Let's forget about unipotency for a second. So this picture solve slightly relaxed problem. So you just forget about unipotency and you just consider upper triangular matrices, which is by our operation BAB transpose remains upper triangular.
Just a second, I'm a little bit confused. So maybe I missed something. So you first said that core rank of Poisson structure is integer part of n over 2. And then you are described as the symplectic leaf of that. So core rank
Of symplectic leaf of GLN.
no, but you have space, this bundle space, and you said that rank is n integer part of n over 2.
That's right, yeah.
And so this means it's not symplectic in general. But then you to obtain something symplectic, you put the Casimirs to be some values, or what happens? It has core rank. Maybe maybe somebody else and
So kind of what's so in the space AM, current well is
it's core rank of
part n over. So it's core rank of this bundle break.
But the AN cross AN is symplectic, this thing that you are considering. The set of matrices B.
Set of in subset of matrices B, it is symplectic, but our map is it's not birational, so it has like fiber.
But it's 5.
So, and in our case, in AN cross AN, the image is not the whole thing. So kind of we have here something.
Yes,
selected,
yes.
It's mapped here, but it's mapped inside. So it's not like
Ah,
it will just the image describes some symplectic thing here. Some symplectic. Okay, so what I'm trying to do now is kind of consider slightly relaxed problem and describe it in terms of such graphs using Foggencher of parameters. So, well, schematically, I don't know if it helps or not. So this red line shows us the transport matrix, which describes the matrix B, and this yellow loop, it sort of described as matrix A, and matrix A tilde is described by this another blue loop. It goes like that. And to organize these loops, we have to glue this bottom part with the top part, which kind of glue this element here with element here, but kind of cross. So it's sort of looks somewhat like Foggencher of construction, like when they parameterize flat the space of flat connections, but except that it's not flat connection, and it's this the surface that you get is sort of Möbius strip. So it's not quite clear what the geometric object is parameterized by this construction. Well, remark that in that way we will get solution of our compatibility condition, but when we forgot about unipotent matrix. And now kind of following Donald Trump, so let's say, let's make the A unipotent again. So the picture that we get is kind of following. So this is a set of parameters which is described by such mesh, and this mesh gives us Poisson bracket. And what the claim is that now we can, there are some Casimirs in this picture. And we will use Casimirs to make our matrix unipotent. So we can fix the values of Casimir such that the matrix becomes unipotent. Idea is like following, that we can this paths, they describe Casimirs. So you should understand this path is just a product of elements. Well, there are paths which kind of small numbers. I don't know if it's possible to see or not. At each vertex, and here, for example, is 1, here is 2, here is 1, 1, 1, 1, 1. It means that such picture means that you have to take product of parameters degree 1 here times the product of square of parameters here times the product of parameter here, and so on. So it's just monomial. This monomial is Casimir. Yeah, also note that this element is glued to that one. So in the picture, these parameters describe some Casimir, and it is easy to compute because everything is log canonical. So this computation of Casimir is sort of, you just solve linear equations. So, and we can describe the collection of all possible Casimirs, and then we see that all Casimirs are described by such strange pictures like that, that. And Casimirs has one sharp angle on the left side or on the right side. Condition that we start with unipotent matrix and we end up with unipotent matrix is written, it can be rewritten exactly in the terms of fixing the value of these Casimirs. So, so we have to do some simplest Hamiltonian reduction. We just have to fix the values of the corresponding Casimirs to something, and and it results in the following, that we just have to get rid of the left side of this mesh and on the right side of this mesh. So if we strip our mesh from the left side and the right one, so this is a picture, the typical picture that we get. So in particular for the case n equal 3, this is the situation. So we'll get 6 parameters. As we described before, it's exactly correspond to dimension 6 that we found before. And it gives us some cluster structure on the describing this symplectic leaf in matrices B. And in symplectic leaf also in the product of A3 times A3.
So the number of Casimirs is equal to this integer part of N over 2? Or?
No. It's slightly bigger space. The number of Casimirs is sort of twice. Well,
No, but
we did some modification of this space.
there are left Casimirs and right.
Yeah, there are left and right.
But for each of them, you have about N over 2 of them, or
Oh, it's kind of each, it's slightly bigger space because of this parameterization. So it's like extra torus here. So we get like n Casimirs on the left, n Casimirs on the right, then we have to strip it. Okay, so how I have like how much time? 1 minute. Okay, then Volodya, sorry, I have to skip this cluster mutation stuff. Okay, just to finish quickly. So what, well, there are something which is cluster mutation. And what I'm saying is that under cluster mutation, well, this is basically you replace one coordinates with a simple change to another log canonical coordinates, and quiver also change. This quiver is equivalent to that one, which is very well known in cluster algebras, like it's so-called cluster quiver of finite mutation type. Now, old folk Chekhov construction embed quivers, embed Teichmueller space with holes into symplectic groupoid. So basically, for case genus 1, for torus with one hole, this construction is like that. Instead of, you can describe torus with one hole by the following fat graph. And this fat graph has parameters. Geodesic functions are described by these formulas. So, and the map from the Teichmueller space to the upper triangular matrices is like that. So, you have this graph, and the G12, for example, is the following loop. We just follow the kind of arc1 and then for arc2 to make a loop. So each loop is equipped with a corresponding geodesic function. If you construct such a matrix, then this is Poisson embedding from the Teichmueller space into space of such matrices. Markov element has a meaning here. It is just a geodesic length of the whole of this torus. And the result is the following. So if you consider this quiver, then we know that from this quiver describes a pair of compatible upper triangular matrices, A and A tilde. A correspond to the one torus with hole, A tilde correspond with another torus with hole. And conditions that Markov elements are equal, Markov functions are equal, it means that the length of the hole of top torus is the same as the length of the top of. So you can glue them together. And when gluing, you introduce one extra parameter of gluing, because you can take this top part and rotate it with respect to the fixed bottom. So remember that I said that the image here is 5-dimensional, but this extra parameter increases kind of the number of parameters by 1. So this thing is 6-dimensional, it's Teichmueller space of closed surfaces of genus 2. And then we have natural guess that this quiver has something to do, and it's actually the case. So, but if you allow 1 more minute, one.
well, I took this.
Yeah, so yes, but we won't have time for questions.
You can.
That's perfectly fine with me. So there in this Teichmueller business, there is this then twist thing. So then when you have a loop, you can do the following operation. You can cut your surface along the loop and then twist one part 360 degrees and then glue it together. And kind of what we want from our construction is that the dent twist has cluster representations. That the dent twist can be obtained as sequence of cluster mutations with respect to our cluster algebra. this is our genus 2 surface with a corresponding choice of generators of mapping class group. So, and it's true for almost all den twist except for this green one. And to make the den twist of green circle also be cluster, we need to do the following modification of this quiver. We have to do this old quiver and add one extra variables and apply one relation that, well, this thing has one Casimir, so we require that Casimir is equal 1. Then for this quiver, the mapping class group is sort of cluster because each element of mapping class group is represented by cluster mutations. And kind of the main result is the Teichmueller space has this cluster formulation in the following form, that it's the corresponding kind of regular function on X7 factored by conditions that Casimir is equal to 1. And thank you. Sorry for overtime. I stop here.
Sorry, we don't have time for questions. So our next speaker is Volodya Fok. He will be talking about Steinberg symbols.